Okay, again, welcome to Physics 10. I know some of you are not here. This is less than half the class. I know that for a fact. And it's a good idea for those who are not coming live to actually subscribe to the channel. What happened is usually I work on the video, I upload it, and usually it sits for a long time in YouTube before YouTube makes it available. And before I can get the link as at that point, but it will not give you the preview when I go to Canvas. So I'll wait for that to become available on YouTube before I actually go and create the announcement on Canvas. By that time, the video may have been there for a long time. I mean, sometimes for hours in it. So it's a good idea that you guys, the ones who are not going to be live, of course, to be subscribing to the channel. That way, you will get a notification from Google saying that there is a new upload if you're interested. The rule, if you guys did not catch it really in terms of how the files are named, because I have several classes are, usually the first letters are the class name. So if you don't see your class in the announcement from Google, you just skip that because that's not your class. You will see PHY10. That's your class, basically. That's whatever content is. So if you're already caught up in terms of what you need to do, you don't worry about it. But if you're not, you probably should go right away on it because, as I said before, there will be discussion sessions immediately following the class where we cover some material. If you are live, you should be able to answer those questions easily, or that question easily, depending on how many there will be. And then if you are, again, if you did not attend the live session, then the only chance for you to really catch those and don't miss on your participation is to actually to watch the whole video. That way you are participating with us, whether you're here in class live with us in session or not. And then you're also following the materials. You're doing everything you're supposed to be doing in terms of meeting all of your requirements. There is assignments, there will be quiz. There is a quiz already that went, and there will be another one this week. This is our second week. There is actually exams that are coming soon. So there are a lot of things that needs to happen. And the worst thing that can happen is to delay your work until the exam time and start thinking about the content. At that point time, you will find hours and hours of probably video if you want to do video, or pages and pages of content that you need to cover, which is too much. So I would like you guys to be on top of it. All of these discussion sessions, they're actually they have due dates on them. So you really have to get also on those due dates too, to make sure you meet all of the grades and things like that. And you've probably seen me already, I mean, in terms of putting things in there in terms of dates and rubrics and how things are graded and so on and so forth. For every assignment, there is a rubric. So I hope that you guys are on top of that in terms of that thing. Okay. So this is just a reminder. Another reminder that is critical always, when you're given an assignment, I know some of you are already in Physics 11 with me, when you're given an assignment, try to start on it as soon as you can. Do not delay that to the last day or the last basically few hours. Then you discover, hey, there is a lot to do in this case, and it's impossible for me to complete in this remaining time. So you really have to start on the object, at least to give you an idea of what it takes. Then you probably have a plan that you have written, or at least in your head, on how to tackle this, and then you start basically coming up with things. Leave things toward the end, and at that point, you really are going to have issues trying to complete all the tasks required to complete that assignment. So this is actually a good practice to do in any class. It's not just in this class as the ones I teach, is to always start on whatever is given to you, especially we are in the online era. I mean, if we are face to face, you will be with me, so we'll make sure that everybody is basically in pace together. But since we are online and there is some sort of a freedom in here, the recommendation here is to start on it as soon as you can, so that you're ahead of your content. So those are just a couple of reminders I wanted to have everybody to be aware of. The first one is, it's a good idea for those who are not live to actually subscribe to the channel. That way they get the content immediately and they don't lose on the participation in terms of the grade. And also in terms of assignment, to start on them right away. That way you're where you need to be, okay? So those are a couple of things I wanted to have before. And today we're supposed to be covering chapter 4, unless you guys have any question from the previous chapter, which was kind of light chapter, to be honest with you. So that was not really hard. This was really about motion, the one-dimensional motion, which was a topic that Mr. Galileo basically has done a lot, extensive work in it. And we discovered from that chapter basically the concepts of velocity and the concepts of acceleration. And those are the two critical concepts that we received from those two, from that chapter. Now, as I said before, Mr. Newton basically inherited the laws of, or at least the studies of Mr. Galileo, and he was interested more of what causes motion than the actual motion. There are two branches of physics. One of them is called kinematics, or the study of motion by itself. This is actually what Mr. Galileo has done for us. He was studying motion. He didn't care about what causes it, what the roots behind it. And then there is another branch of mechanics that is called dynamics. Dynamics is really the causes of motion, what causes motion to begin with. And that's what interested Mr. Newton. Mr. Newton was interested into what causes motion. So we already discovered the first law, and the first law says basically that if you have a single object, and that object is by itself in the universe, or you have many objects, and those many objects can be isolated to appear as if that they are by themselves in the universe. If those objects are not under net forces, then those objects basically will continue in their direction where they were moving with the same speed. So velocity as a vector, which we learned as a vector, is constant both in magnitude and direction. That's basically what the first law is saying of Mr. Newton, and which is really verbatim what Mr. Galileo has done for us. This is actually Galileo's work. That's what first law was. The second law, we will learn about it, is a cause and effect relationship. This is we're still dealing with an object, a single object, but that object happened to be under net forces, okay? So this object now is under net forces. That object, the V equal to a constant, is no longer true. V will change, and will change in one or two ways. Either change in magnitude or change in direction. As a matter of fact, it can change in both, okay? And that is the acceleration. So an acceleration will all of a sudden appear just because the object now is under net forces. So the result of the fact that I now have forces is the presence of an acceleration. The reason why I did not have acceleration in the first law is because there was no forces. Now we have forces. That is the cause. The effect is an acceleration, which is change in motion. And this relationship is proportional. That means you double the force, you double the acceleration. You'll get twice as much effect from twice as much cause. You have the force, you have the cause, the effect also is halved. So that's basically what this relationship is saying. The trouble with it is, if you only can afford, let's say, for example, 10 newtons, and you would want to push, for example, with it a mouse, it's probably easier for you to push a mouse than to push an elephant, because the elephant has more resistance to the 10 newtons than the mouse does. So a property in here is needed, and that quantifies the resistance of the object to the change in motion. So this is the relationship and how it emerges. A, which is really an effect. This is the result, if you wish. F, which is the force, which is the cause. That's what makes things happen. And now, in between those cause and effect relationship, there is actually the object itself and its property of not wishing to change its state. If it was at rest, it wants to really want to stay at rest. That's because of its inertia. If it was moving, it wants to continue moving. So if you want to push it further in its motion, or change its direction, or slow it down, it doesn't like that. It doesn't like the change in motion, and that is its inertia. So that's basically how this relationship is written. And in a nutshell, this relationship can be written actually algebraically also in a different format. Basically, F equals to ma. It's the same thing. I mean, the first format is more actually saying than this one. This is how people know it, F equals to ma. This is really, in terms of physics, this is the law. This is the most important law that you can do a lot of things with it. Because even when we discover the third law will resolve itself into this one. The first law can be actually understood in this sense too. So basically, that's the context that this is why it's called the law. The premises of this law is you have one object and their net forces. That's it. Then this will apply. That there is an effect in this case, which is the tangent motion, and this is the result of and net forces. So F in this case is not necessarily a single force. It could be many forces applied on the object, but they resolve themselves into a resultant, into a sum. And that sum is this expression, this F. This is what we call net force. For those who are sitting in physics 11, this is what we call the resultant, which is the sum, okay? And I think we did that also when we talked about it in chapter 3 in here in this class too. So this is the resultant, which is the sum of all of the other forces. Basically, one pulling this way, the other one is pulling that way, the other one is pulling this way, the third one is pulling upward. And the combined effect of all of these forces is this force that we're talking about. It could happen that all of them, they will cancel. At least their sum will cancel. One is pulling this way, the other one is pulling this way, and the object is actually in equilibrium in this position. It's not going anywhere. So what we do in this case, we go back to the first law. Because in this case, the net forces are zero, so we resolve it back to the first law. I think this is basically, first of all, this is the entire chapter. It summarizes into this expression. You can talk and say F equals to ma. By far, F equals to ma, it is the most important concept that you will learn in this class. Physics 10, if anything at all you will learn from it, is this expression, F equals to ma. If somebody asks you, did you learn from physics 10? And you tell them, oh, I learned force causes the change in motion. F equals to ma. Objects resist that change in motion. That's their inertia. If you say it this way, you would have gone, you have done everything. This is it. This is, you have, in a nutshell, stated exactly the most important concept in this class. So this is by far the most important one. You probably have to pause at this point if you're watching this video, or if you are in class 2, take a note of the time, the day and the time. Today is September 3rd of the year 2020. We're still in COVID times. At 4:12 p.m. This is the day you discovered the most important law in physics. Okay, this is by far the most important law in physics, at least in the day-to-day experience. I mean, somebody will tell you, okay, how about E equals to mc squared and other laws in physics? Well, those are probably, we deal with them in other levels. But from my daily experience, this is by far the most important law. The second law of Newton. This is really, it summarizes everything. The promise with it too is, of course, combined with the other two laws, you could solve any problem in physics. You could take any problem and basically break it down, understand it, and solve it. Do you guys have enough of this infomercial, or should I continue? Are you sick of this story now? Okay, continue. Okay, good. So basically, the point is, F equals to ma. There is, I'll be honest with you, I can talk in here for a whole day on it, and it's probably not going to be enough, honestly. I mean, it's a great law, and what I'm hoping that you guys take from this one is how important this is, and I'm hoping that you will remember this if you don't remember anything at all from this class. If you take nothing from this class, at least you remember this thing, okay? So, if you guys are not, if you're willing to move, let's get into the topics we'll be covering into this chapter. So this chapter will talk about, again, forces cause acceleration. That is exactly what we've been saying. F equals to ma, okay? There is a cause and effect, causality in this case. One comes after the other, and one is an indicator of the other. If you see an acceleration, an object that all of a sudden has picked up speed or slowed down or actually went on a curve, you must conclude then there must be a force that caused this change in its state of motion. So that's basically how you go about this analysis. That's basically how this thing is. That's how you study motion in general. Okay. If in case something happened, and yesterday it happened with me in another class, not with you guys, the somehow this session gets broken down because of the internet issues, please stay with it. I will come back if worse comes to worse. I will use my phone. Okay. Hopefully you guys get this message. Okay. Very good. So the second concept that we're going to be discovering and talking about is friction. Friction, in a sense, is a blessing and also is a curse in the same time. It's a problem in physics that we have to deal with, and sometimes it's an undesirable issue that we have to contend with all the time. Okay, and sometimes actually it's without it nothing can happen. As a matter of fact, you cannot move right now. You cannot go anywhere without friction. You don't believe me? Go on an icy day. Try to walk, try to run, or drive. It won't work because friction is less at that time. And if you cancel friction completely, lift a person and try to have him walk because there is no friction. So friction, I mean, when you go to the garage and they would want to work on your car, they lift the car up and they spin the tire, and then the engine is running so hard. But the car is not going anywhere because there is no contact between the tire and the ground. And at that point, so it's not the engine that really makes the car move. It's the tire. It's the earth, actually. The asphalt, the one that makes the earth move. So it's the friction. So sometimes it's desirable, sometimes it's not. If you're in auto racing, you would want to have as much traction as possible so that the car can move. We'll talk about something which is sometimes confusing, mass and weight, especially here in the United States because we use pound for both mass and weight. And there is a distinction that you really have to make that clear to you guys. Some of you probably this is your last class of physics that you will ever have, and you really also have to have that in mind, that there is a big difference between a mass, which is the ability of the object or its resistance to a change in motion, and the weight, which is the force exerted by the earth on the object. So one of them is a force, which is a vector, and the other one actually is a scalar, which is a number. If you want to see the difference between the two, take the same object and put it on the moon. It will have a different weight, but its mass does not change. The mass stays the same. So if somebody tells you, okay, the person weighs 110 pounds, for example, or 140 pounds, and that's exactly how much his mass is, well, if you take that person 140 pounds and put him on the moon, all of a sudden the 140 pounds will weigh less. Did he all of a sudden, let's say, for example, he weighs 60 pounds. Did he lose already 80 pounds? No. He didn't lose any mass whatsoever. His weight's changed, that's all. But his mass stays the same. And because here in the United States, we append the same number for both. We say this is, and that's kind of confusion, but the matter of the fact is that there is a discrepancy, there is a difference between the two, and the difference is actually in the standard system of units is the force of, is the gravitational G, the one that we discovered last time. Then we state, of course, the second law, which is the objective of this chapter. And then we'll talk about the free fall, which is a daily experience that we can see. And then we'll talk about the non-free fall, basically fall here at the value of G. And in here, fall when there is resistance. You fall not just at the weight, you fall at with the resistance, like, for example, the parachute, or when the lander drops on Mars. It's not completely free fall. You don't want it to be a free fall there. You want it to be a non-free fall. You want it to be controlled fall, if you wish. Same thing with the parachute. You don't want to drop yourself from a plane coming on a free fall, because then you're going to hit the ground with a high speed that's going to cause damage. You would want to control that descent. Okay. This is the chapter in a nutshell. Okay. So again, forces is acceleration is directly proportional to the force. I mean, this is, you can, this is based on observation. This is based on experiment. You apply force and you see how much it gains in terms of velocity or loses in terms of velocity or changes direction. So force, this symbol in here is not equal. This symbol in here is proportional. Okay. So you double the force for the same object. you get twice as much acceleration. Okay, that's what you do in a lab, by the way. You have to identify the variables in the problem and fix everything else and just change one of them. So in this case, the independent variable is the force. That is the one that you can vary at will, okay? And the dependent variable in this case, the one that depends on the force, is the acceleration, okay? If you apply 10 newtons, for example, on an object that is 1 kilogram, 10 Newton divided by 1 kilogram, you will end up with 10, what is it, 10 meter per second squared, okay? You double the force to 20, and now all of a sudden the acceleration doubles. So there is a one-to-one correspondence, and if you graph this data, it looks like a line, okay? So that's basically how A as a function of F is, provided we have the same mass. We did not change mass. Of course, if we change mass, we're not looking at this experiment. We're doing some nonsense in here. If we're going to change mass, we have to keep at least the force constant. If we keep the force constant, then we'll check how is the dependent variable in this case, which is the acceleration, changes with the independent variable in this case, which is the mass. Double the mass, put more weight on it, and see how much, provided you maintain the force the same. Okay, so one of the other two has to be done in a different way. So this experiment in this case basically gives you the acceleration is proportional to the net force. Okay. The force of friction, which is actually one of the experiments that Mr. Galileo has played with, and that's because, as I said, the issue was Aristotle thought that the rest is actually the state of the normal state for this, for example, object. So when he smoothed the surface further and further and further, that's when he stated that, okay, it's really because the force of friction is the one that is stopping the object. The object has tendency to go forever and ever, at least on the normal surface. And it gains speed from the incline due to the force of gravity. So the force of friction in here, which is a real force, and we deal with it on a daily basis. And it's actually the interaction. So if you rub my hand, for example, against one another, the interaction of the electrons of one side of the surface with the electrons on the other side of the surface, basically. And that's what you see in here as being the friction. If you rub your hand very fast, you will see them that they start to get warm. Actually, that's one of the consequences of friction. It's related to heat, okay? And in your engine, for example, energy is lost most of the times to heat, which is coming from the friction, from the moving parts inside the engine. So it's kind of a stickiness when objects stick to one another. If you put a lotion between your hands, you will have less friction in this case, less heat. You need to rub very fast in order for you to generate friction. Friction is related to velocity, okay? Friction really opposes, does it look like this? Velocity. If an object is not moving, there is no friction. The object starts to move or intends to move, then there is friction, okay? Yes, it's a force, so it needs direction, Kyle. Absolutely. This is a force. So if the object, for example, let me remove all of these things in here. Can I go back in here? Or it's not deleting? Okay. Can go further. Okay. So let's say, for example, I have an object that is sitting still in here and minding its own business, and I push it with a force of friction this way. Okay. If it were to, with a force, I'm sorry, with a normal force. If this object were to move, intuitively, I think it's going to move this way. You guys see that? So the force of friction must be opposing either the actual motion or the intended direction of motion. If this object doesn't move, because this desk, for example, I'm pushing it right now, it's not moving. So I cannot say it's opposing the direction of motion because it's not moving. In this case, it's opposing the intended direction of motion. So the friction must be this way. You guys see that? If I go on the other side and push it, it's going to oppose the intended direction of motion, which is coming toward me. So the force of friction always points away from the direction of motion or the intended direction of motion. So that is, and that is V actually. F of friction and V, they go one in one in direction. In magnitude, sometimes there are all kinds of frictions, so that you guys know. At this point, probably there is a static friction, like this one is called static friction because the object is not moving. So this static friction, what it does, it keeps it from moving. There is kinetic friction. Kinetic friction is the object is in motion and it opposes actually motion. And then there is viscosity, which is another kind of friction. And that if you take, for example, a cup of water and you spill it, and if you take honey, for example, and you spill it, you will see one of them flowing much more easily than the other. So one of them is more viscous than the other. So the viscosity is another kind of friction in this case, and that is the interaction of the fluid with the sides and it's all of its elements. And you can see if that's why, for example, oil comes in different weights. For example, when you go and change your oil in the car, they come in different weights, but because of the viscosity, one of them is suitable for the hot air and high altitudes or lower altitudes and lower temperatures and so on and so forth. So you'd want to have the right viscosity for your car when you go and change the fluid. So that's also another friction. And then there is another kind of friction, and all of the first two, they don't depend on the magnitude of the velocity, but they depend only on its direction. The second one, the viscosity, actually depends also on the magnitude in addition to the direction of the velocity. And the third one that I'm going to talk about, or the fourth one that we're going to see actually in here, it's called the drag force. And the drag force is what parachutes experience when they're coming down. And that is actually proportional to the square of the velocity, in addition, opposing the direction of the velocity. So friction, wherever you see it, it has to do with velocity, okay? If the object is not moving, there is no friction, provided you're not dealing with static friction, okay? If you're dealing with static friction and there is an applied force, then in that case, actually, there is a friction. That's opposing the intended direction of motion. There was no motion in static, but intended. If this desk were to move, it's going to move forward, so the friction is pushing against my push. But then, when I stop pushing, there is no friction at that point. I'm not pushing on the desk, there is no friction whatsoever. The object is stationary and I'm not pushing against it, okay? If you try to move your refrigerator, for example, today when you go home, when you are at home actually, when you push on the refrigerator doesn't move back. Even if you don't, even if it's not nailed against the wall, even if you try to move it across the room, it's still not going to budge unless you apply big enough force. So during your push, initial push, the refrigerator is being held in place by friction, and the friction is actually working against you, okay? So, the force of friction can occur with sliding objects, absolutely. When objects slide against one another, and I just gave the example in here, actually the force of friction is between the desk and the carpet in here, okay? That's the force of friction. And in water also, yes, I gave the example of the viscosity. Viscosity actually also is another kind of friction. And that's why water takes heat, for example, and used, for example, in cooling systems. In air too, yes. And that's why, for example, what you see, for example, the falling stars, they call them the falling stars, shooting stars, they're actually burning because they hit the atmosphere and they go at tremendous speeds, and they actually, that's heat too, that's friction. So it's everywhere. Friction is everywhere, okay, in all of these situations. So the correct answer here is D. Okay. So I just gave the example of here in this case is the crate. When son J pushes a refrigerator across, I'm not sure if I said the name correctly or not, so I'm sorry if I messed it up. When son J pushes a refrigerator across a kitchen floor at a constant speed, the force of friction between the refrigerator and the floor. Here the key word to look for is this. Constant. If the crate now is accelerating, the refrigerator is accelerating, then that's not the same. If the refrigerator is decelerating, that's not the same. But it's constant speed, that means the net forces are zero. But it's pushing, so the friction must be pushing by the same force so that the two cancel, because then the first law applies. In this case, there is no acceleration. Okay? So in this case, equal to Sanjay's push. The correct answer should be this. When you're reading questions like this one, especially you have quizzes and exams coming, pay attention to every single word, okay? And there are some key words. This is one of them. Constant speed, okay? And that's because the first law now applies. Now, when Sanjay pushes the refrigerator across a floor at an increasing speed, now it's accelerating. I can't say that his force. So he's pushing with a force. The friction is still pushing against him, but now he's gaining more and more speed. So his force must be greater than the friction. So in this case, less than Sanjay's push. So the correct answer, the friction should be less than that. So the correct answer should be A, isn't it? Yes. Which question, Jeffrey, you thought it's C? This one or this one? Oh, you're right. You're right. The opposite direction. Yeah, I'm sorry. You're right. You're right on that. Okay. So the correct answer, I mean, they're not equal because in here they're taken in the sense. And that's why it's a good point that you raised, Jeffrey. I'm glad you did that. Because the drawing, I had them drawn equal in magnitude and opposite in direction. And that's the correct answer, is C in this case. But they're equal in magnitude. That's what I meant to say. But this wording in here and again is sometimes tricky. Equal when both of them actually have the same direction. Does this make sense? Very good. Okay, I'm glad you raised that point. Okay, so the correct answer is C because the verbiage again. Okay, sometimes this questions can be tricky, and this was one of them. Okay, so the correct answer is they're equal in magnitude as we drew them correctly in here, but as we drew them also correctly, they're opposite in direction, so they cannot be equal. This is what B has intended for meaning. Okay, that's not correct. Okay. Does this make sense, or did I guess confuse you? Okay, good. Thank you, Jacqueline. Okay. Sometimes the drawing is, but that's a good point that Jeffrey raised in here, in the fact that you have to really read the question carefully and read all of your options and see which one is really correct. Sometimes two of them may look correct, but one of them is more correct than the other. Okay. And in here, I made already a big fuss over the mass and the weight, especially here in the United States, and complained enough that probably I will get a letter tomorrow from Congress stating that, what, you want us to change units now to the SI? I hope they do, actually, so that we have no problem. But anyway, the mass, again, is the quantity of matter in the object, and it's a scalar, it's a number. And it's a positive number. That's one of the things that we know about masses. They are always positive. And also, they represent inertia, how much an object opposes the change in its state and motion. Weight, okay, is the force of gravity, how much is being pulled toward the earth. Again, we use pound here in this country to represent both of them, and we append the same number. So if you go and buy 10 pounds of potatoes, you're carrying with you 10 pounds of force and walking with it from the car to the car. Then if you are on a different planet, if you are, for example, on Mars, you buy 10 pound, but it feels a little lighter than the 10 pounds, feel like 8 or 7 pounds, because again, the force of gravity on Mars is less than that of the Earth. But because of our daily experience, we append the same number. That's why in SI, there is the difference between them is the weight, which is represented by W, is mass, which is represented in kilogram, times G, which is 9.8 meter for every second per second, okay? So that's, roughly it's 10, okay? So roughly it's 10. So 10 pounds, which is about 55 kilograms, times by roughly about 10, is about 50 newtons. That's how much you experience the weight of 10 pounds of potatoes, for example. if you take the 10 pounds of potatoes and probably put them on Mars, you would feel, let's say, 30 pounds, or 30 newtons or 35 newtons, okay? You will feel them lighter. And that is basically, there are different numbers both for the force, which is weight, and for the mass, which is the mass, basically, okay? For you guys, like I said, this is probably your last chance taking a physics class, so you really have to think about this and make sure that this is clear. And always take the example of the Earth Moon as an example in your head in your approach. Okay, so mass, a measure of inertia of an object, independent of gravity, greater inertia, greater mass. Unit of measurement is kilogram. Okay, and then the weight, usually a force on an object due to gravity. Scientific notation for the unit is Newton, which is N. Also, we use a pound for it. Okay, that's also another way of using the weight in here too. So if the mass of an object is halved, its weight is halved. Okay. So there is a one-to-one correspondence. Okay. So the expression to go by in here is W is equal to mg. This g is the same for the entire planet. Okay, more or less. It depends on the height, depends on the latitude and the position with respect to the equator, but it varies very little actually. But double G, double W, I'm sorry, G stays the same constant. Or half it, okay? So if you have an object and all of a sudden it splits into two pieces, each piece will take half the weight because it took half the mass. So this is I already was talking about, and this is the key thing that you probably have to put in mind. Always think about the moon. So the mass on Earth and the mass on the moon is the same thing. What changes in this case is the weight. One kilogram weighs 10 newtons. Again, because 9.8 newtons, that's more accurate actually. And the relationship is between the kilogram and the pound is 1 kilogram is 2.2 pounds. And 1 pound, which is 0.445 newtons, 1 pound, which is, I'm sorry, 0.45 kilogram, and you multiply it by 10, you end up with 4.45 newtons, okay? So this is the weight, the 1 pound weight, not the 1 pound mass, okay? Same thing in here, because you see it in here in newtons, but this is actually kilogram. There is a problem in this relationship. This equality doesn't pour through all the way to the other end. So when we pull slowly on an object like this one, the top string breaks, which this illustrates, because again, you're pulling, you're allowing for the mass actually to also pull. So in this case, you're pulling with the combined forces of your own pull plus the weight of this this ball. So in this case, this part will break, okay? And then I think we talked about this experiment sometime in the past. And when you pull suddenly, on this case in here, when you pull suddenly, you don't allow for this mass to give it a chance. So in this case, it's going to resist the change in motion, in which case it's going to oppose that. So the force will be pulling on this way, the one that you're pulling with, and this is actually holding it back. So in this case, this is the inertia, the mass of the ball, okay? We already talked about the acceleration, the fact that I cannot push the mouse, for example, with the same force and expect the same result as an elephant does. So all if I can do is, for example, 100 newtons, and I want to apply it to a small object, for example, a toy and a big car, then in this case, the object will move easier because it has less mass. And that's why inversely proportional to that. That's where the constant of proportionality in this case. Again, this is not equal or approximately equal. This is proportional, okay? If the mass doubles, the acceleration goes by half. If the mass goes by half, the acceleration doubles. That's basically the what this expression is telling me. Here is an example with Newton. Isaac Newton was the first to connect the concept of force and mass to produce the acceleration. And that is basically the law that we discovered, that we talked about, the second law, F equals to ma, or A actually equal to F over m, more of what it should be. This relationship is vector relationship. This is not a scalar relationship. Namely, the force is a vector, the acceleration of the effect is a vector also. The scalar in this equation is actually m, the mass. That is a number. The other two are vectors. He formulated this law while he's still actually in student. He was still in college, basically. And he was in his early 20s when he did that. So he was very young when he did that. So Newton's second law, the acceleration produced by a net force on the object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. If anything, like I said, that you can take from this class is this statement, okay? You can take it in this way or whichever way you feel about it. But if you're going to say F equals to ma or A equals to F over m, you have to be able to support what that is. There is a cause and effect relationship. The cause is the force. The effect is change in motion, namely the acceleration. And the inertia in this case measures how much an object resists that change in motion, okay? So that's basically how this expression can be read. Can I have thumbs up on this law from you guys? Okay, Jeffrey, Samantha, V, Kyle. Other guys, you don't like it? Okay, Taryn, Patricia, Isaac. Okay, Caesar, Joshua, good. Juan, Vanessa, Arturo, Ali. Still have a few people who did not. Okay, a few people who did not think that this is probably. Okay, if tomorrow police officer stops you, okay, and tells you you are in violation of the law, tell him how, because this is the law I know. How could I be violation of F equals to MA? Okay. Don't mention my name when you do that, okay? Because if you're gonna be in trouble, I don't want to be with you, okay? But this is the law, okay? Actually, Kyle, you can say that to the judge too, okay? And explain to him there is no way it could violate the law, okay? That this police officer doesn't know what he's talking about. So don't bring me as a witness, that's all. Okay, anyway. So this is again a restatement of that law, okay? And this is if net force acting on an object is doubled, then the acceleration will double. If the mass is doubled, then the acceleration is halved, okay? Because it's inversely proportional to that. Here again, the same concept in here. You push with the same force on an object, it gains acceleration. You twice the force is going to basically get twice as much acceleration. And then if you basically put two bricks in this case, you're going to end up with half the acceleration, and you put twice on the object. So basically you see what this relationship is saying. Basically it's the same thing, except it's in this representation. If you are math inclined, it's easy to say A equals to F over M, okay? If not, this is a good picture, good representation for that too, just to reinforce the same point. So consider a cart pushing along a track with a certain force. If the force remains the same while the mass of the cart decreases to half, the acceleration of the cart now all of a sudden increases to twice. Again, because if the mass, let's say for example, was 1 kilogram, whatever that force was, and the acceleration will be that. So now if this number all of a sudden is 0.5, you divide by 0.5, that means you multiply by 2. So the correct answer should be C. Okay. The mass of the cart doubles, no, okay, what is this one? Push a cart along a track, but twice as much force on it if the acceleration remains the same. Aha, we have a problem now, okay? We have a problem now. We doubled the force, but the acceleration we saw, it stays the same. So we met 2f, but the acceleration did not change. So something must have happened to the mass in here. So all of a sudden, somebody put more groceries in the cart in here, okay, and doubled the mass, so that the 2 drops, okay. So the correct answer should be the mass of the cart must have doubled. Again, there is that cause and effect relationship, okay? You're looking at the fact what happened and looking at the cause. The cause doubled, the effect stays the same, so you have the third culprit in here, the third party in the equation, which is a mass in this case that plays a role. And this is actually what Mr. Galileo has demonstrated with the object that he dropped from Pisa Tower, basically with the twice the force, twice the object, G stayed the same. So the object should land on the ground the same way, provided he did the experiment on a day when the air was very calm and very little friction. Then you can actually see that they will drop at almost the same point, because still we still have friction to deal with if you're doing it in Pisa. Okay, this is a question that I need you to, when you come back to the discussion after this class, to answer it in the discussion. Actually, the discussion is open right now. There is already a place for it. So if you're watching it live, you should be able to answer this question and put it there. So what we have in here, at one instant, an object in free fall has a speed of 40 meters per second. Remember, in free fall, we gain 10 meters per second for every second, or 10 meters per second squared. So he's already moving with 40 meters per second. And now after another second, the object will gain another 10 meters per second. So the correct answer should be C. Is this correct? Yes. So question 1, when you go there, you could put either C or C, 50 meters per second. It's up to you, okay? But we know the answer to that question. So the first question that you guys have for the discussion after this one is 50 meters per second, parentheses C, okay? So you can put that question. Now, if you're watching it not live, you still have the same benefit, basically, and go there and do the same thing. It's still open there. Now, you cannot see other people's answer unless you actually post yourself, and you're not allowed to edit or change your answer after it was posted. So please make sure you abide by the rules, otherwise you're not going to be credited for your work. Is everybody okay with this one? So this is the free fall. Okay, very good, V. We have a 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest, from negligible air resistance. So the air resistance is negligible. If the air resistance is important, then we have a problem. The acceleration of the heavier ball will be less than, the same, or more. So it should be the same, because again, we just argued from the previous diagram that if you double the mass or you halve the mass, doesn't matter. The acceleration is always g in this case, okay, which is 9.8 meter per second squared, or approximately 10 meter per second squared, okay? It's the same thing. Some people already are posting on this thing. My watch is telling me that you guys are already posting the answers, okay? We're not done though. I hope that you did not do that yet. Don't post your answers yet, okay? Still have more questions. So if you edit it after the class, it's fine, but provided you edit it around when we ask the last question, okay? I know some of you already posted the answers in there. Yes? Okay, so let's hold on to the last question they asked, then you can go and post these things, okay? A 5 kilogram again and a 10 kilogram are dropped from rest. When the free falling 5 kilogram reaches a speed of 10 meters per second, the speed of the free falling 10 kilogram should be the same, because again, the acceleration is the same. So it doesn't matter how much mass you have in this case. When an object falls downward through the air, it experiences, now I already talked about the fact that there is non-free fall and the air resistance will matter now. So in this case, it's falling not necessarily with the constant acceleration, but the acceleration will change actually and depends on the speed. And the culprit in this case is this force, the drag force. Okay, the drag force is a force that is proportional to both the velocity squared to the area in here. That's why a big parachute will be better than a small one, because you will have more drag force to hold you in space. Okay, and it's proportional also on a coefficient called d, the coefficient of drag, and it's also proportional to the density of the air. For example, if you drop an object on Venus, which has a very thick atmosphere, versus if you drop it, for example, on Mars, which has very low density atmosphere, of course, the big density on Venus will give you bigger drag, so the object will probably stay hovering on the surface, on the atmosphere of Venus, versus is going to continue down unless you have a big area, as I just mentioned. Okay. The Earth has a density of the air which is very, very small compared to that of Venus, but it's very, very big compared to Mars. Okay. So the condition of knee free fall is when the object has the air resistance is non-negligible. You cannot neglect it. Okay. Like for example, the feather. That's not a free fall. Okay. And depends on two things: the speed and the frontal surface. So in this case, it depends on the velocity. That's what I said, v squared. And it also depends on the area, okay? We're doing this experiment on Earth, so we're not going to change the density of the air. That's why it's not mentioned in here. That's why the air doesn't matter. Even at higher temperatures or lower temperature, higher, it varies very little. So it's not going to matter much. And the coefficient of drag is the same for almost all of the objects, so it's not changing. So the only two the objects that matter are the velocity and the area. Okay, ignore the square. Okay, just say the velocity, the magnitude, not the velocity. Because when you square the velocity, it becomes speed. So it's speed, how fast the object is falling, and also its cross section or the area. So an object, as it starts falling, as you drop the object, it has no speed. So at that point, it has no drag. So the only thing that acts on it, its own weight. But as it starts falling, the object now all of a sudden starts to gain more and more speed, which makes the drag bigger and bigger. So now there is a force opposing the gravity, the weight. And that force will start to increase with the speed because the object is gaining more and more speed. At some point, this drag force will be equal to the weight. They cancel one another at that point. So when the two cancel, the net force is zero. We're back to law number one, which says that the object then cannot gain any more speed. We have reached the maximum speed with which we fall. This is what we call the terminal velocity. Terminal velocity is reached when the drag force, or the force of drag, is exactly equal to the weight of the object. And it starts with zero drag force, and as the object gains speed a little, the drag force starts to build up. And as it moves forward, because now it's still not zero, the acceleration, so the object will gain more and more speed in the process. In doing so, it builds up more and more force of drag, and at some point the two cancel. The weight and the force of drag cancel, in which case the acceleration is zero, because it's going to be the net force, which is the weight, okay, minus the force of drag, now that is equal to exactly the weight divided by the mass, and this is zero. So at some point, they cancel one another, and the acceleration is zero. So there is no more gain of velocity after that, after we reach that point. So the object now comes at constant speed down, okay? So if you're building a parachute, you'll have to build it in such a way that the area is big, so that you reach that point very quickly, and you can come as smooth as possible to the ground, okay? You don't want to come with a big velocity. So this terminal velocity, same as terminal speed with direction, of course, occurs when the acceleration terminates, when there is no more acceleration at that point, okay? When air resistance equals weight and net is zero. The air resistance is what I'm calling drag force in this case, okay? So a skydiver in fall after jumping from a plane. So that's the terminal velocity. Weight and air resistance act on a falling object, so they cancel one another. And if you don't have a parachute, you're going to reach a terminal velocity, but probably you're going to reach the ground before you do that. So you still continue gaining velocity up until the point when you hit the ground. So don't try that, okay? As falling speed increases, air resistance on the diver builds up, net force is reduced, and acceleration becomes less. When air resistance equals the diver's weight, net force is zero and acceleration terminates. No more acceleration. Diver reaches terminal velocity, then continues the fall at constant speed. So from that point on, it's a motion with constant speed because the two forces are canceling one another. This is another question that you're going to put in your notes. We're going to go and answer it too. When a 20 Newton falling object encounters a 5 Newton air resistance, its acceleration. So 20 Newton putting down, that's how much force it is. And the drag force in this case, or the resistance, is 5 Newton. So you subtract the two and you divide them by his weight. Because it's 20 Newton, that means its mass was actually 2 kilograms. 20 minus 5 is 15 divided by 2. It's 7.5 meter per second, and that is actually less than g. So it should be the correct answer. It should be less than g. So this is the correct answer that you're going to plug in later on for the discussion. So the second question is A, or less than g. Less than g, or you actually write it verbose, less than g, or you write it A, okay? Parentheses. So this is the second question. We still are not done, okay? If a 50 Newton person is to fall at terminal speed, the air resistance needed is. So we have a person who is 50 Newtons. This must be a very, very small person because 5 kilograms. What is, that's a baby. It's a 10-pounder. It's a newborn, okay? This is a very bad example, okay? Sometimes you have to critique these things. So a 50 Newton person, or he's not falling on Earth probably, he's still falling, but probably on Mars or some other place, okay? Even Mars is still a tiny person, okay? Maybe on one of the moons of, tiny moons of Neptune or something, okay? So let's take it with that. So if a 50 Newton person is to fall at terminal speed, the air resistance is needed is, how much do you guys think? So the key word in here in this problem is terminal speed. That means he's not gaining or losing velocity. That means if his weight is 50 Newtons, the air force must also be 50 Newtons. The air resistance must be 50 Newtons so that both of them cancel. And at that point, the velocity is not increasing. It's staying the same. Okay. So as the skydiver falls faster and faster through the air resistance. So as a person moving faster and faster, that means gaining more and more speed. Remember, the air resistance is proportional to speed. So air resistance will increase with the increasing speed because now he's falling faster and faster. That means he's gaining speed while he's falling. So in this case, the correct answer is A, because again, the air resistance is proportional to the velocity. Okay. Now, as a skydiver continues to fall faster and faster through the air, the net force now has to decrease because his weight is pulling down and this thing is building more and more because there is more and more air resistance. So the net force now, which is the difference between the two, must be decreasing, going down. Okay. This is another question that for you guys to add to the, so there are 3 questions today so far. So please make a note of this question in here for your comments in there, okay? So again, if you're live, you have to take care of this. If you're not live, you need to really watch for all of these questions and know the answers to them and go and post them after the session is over to your Canvas discussion place. As the skydiver continues to fall faster and faster through the air, her acceleration. Now, because the net force, we just saw it decreasing, is going less and less. So the net force also, because the acceleration and the net force go hand in hand. So in this case, the acceleration also is decreasing. So the correct answer to this one in here that you're going to post on Canvas for the third question is B, decreases. Okay? Why is this line coming through? Okay. B, between them. So this is the third question so far that we have encountered. Do you guys understand it though? Because the acceleration, we're just learning about the second law, goes hand in hand with the net force. We just discovered that the net force is going down. So is the acceleration is going down now, also is decreasing in magnitude. Okay, question, consider a heavy and a light person jumping together with the same size parachute. So A is the same, okay, from the same altitude. So both of them have the same initial velocity and both of them have the same equipment in terms of parachutes. One of them is lighter than the other. Who will reach the ground first? Here is the trick. The lighter person will reach his or her terminal velocity quickly because his weight will be balanced sooner with the drag force. The heavier person will need more time to have his weight cancelled by the drag force. So during this stage in here, he's gaining more and more velocity. So the heavier person will reach the ground first, okay, with higher speed. So that's the thing with it. Unfortunately, that's part of the, is this correct? Yes, the heavier person is the one. Because again, he needs more time to reach his terminal velocity versus the light person, okay? So the light person, I mean, case in point, a feather, for example, reaches terminal velocity quicker than, for example, but again, that's your shape is different, okay? But if you have the same parachute now provided, both of them have the same cross section. Okay, these are the experiments for the coin and free, non-free air. Basically, when you have an air, in this case, it's clearly that the coin will fall first because this one will reach its terminal velocity quickly. The other one will continue building speed. And when we remove the air, in this case, there is no air resistance. So they should reach the same point together. Free fall versus non-free. Coin and feather fall in vacuum. There is no air resistance, so there is no air resistance. So both of them will reach the ground first. Okay. Any questions about this one? So those are the three questions that you guys have. Okay. So hopefully you have had a chance to now go. If you did, and I know, hold on, don't go yet. Okay. Let me check quickly in here. Let me see. What in physics 10? And models. Okay, there is 1, 2, 3, 4, 5 people. I'm going to ask you guys to basically, I'm going to delete these posts, if you guys don't mind. Yes, because you have answered too soon, because there are more questions. I'm going to delete this post first, and then you're going to post again, okay? That way it's fair for you too, because I probably said something earlier to give you the impression that probably you go immediately, because if you edit it on your own, it's not going to count. So I'm going to remove them myself, and then you're going to go and basically post these things again. So I removed all of the 5 basically postings. And now you're free to go and answer those questions. There were 3 questions today. Yes? Sounds correct? Okay, you will have a quiz. Hopefully it should be ready by tomorrow. Okay, because I have another class, and after that class I have to take care of some other things, and tomorrow I have some stuff to do. So it should be ready by tomorrow. You will have ample time to take care of this quiz also for this 2 chapters, 3 and 4. Okay. Okay, guys, be safe. I know we have a long weekend. We have a holiday on Monday, so there will be a lot of people going to the beach. Don't go there if there are too many people there. I don't want you to really get hurt because of this COVID thing. And be safe. It's also going to be a very warm weekend according to the weatherman. So also be cool too, okay? And I'll see you Tuesday. See you guys. Thank you. Bye.